Dear students, welcome to yet another session for brilliant online physics classes. Today we are going to discuss one of the important topic in the chapter, electromagnetic induction. Hope you remember the last class topic. Let's have a quick recap on the topic which we discussed in the last class. Last class we got a clear idea about what is electromagnetic induction, and after that about Faraday's laws of electromagnetic induction. Right? Faraday's first law states that whenever the magnetic flux linked with a closed circuit changes, an EMF is induced, and second law is stating that how to find the magnitude of induced EMF, and we got a clear idea that the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linked with it. Hope you remember all these things. And now we are going to discuss a very important session, and that's about how to find the direction of induced current. The direction of induced current, how can we determine in a coil? And for that, there is a very important law. Let's see what is that law. Look at this. It is Lenz's law. So first of all, we should have an idea what does Lenz's law deal with. It is about how to find the direction of induced EMF. Okay, so before going to understand what is Lenz's law, let's go through the statement, and after that we can go to the detailed explanation. Okay, so remember, Lenz's law is dealing with the direction of induced EMF. So how can we find the direction of induced EMF? Look at the statement. The direction of induced EMF is such that it opposes the cause which produces it. Okay, the direction of induced EMF is such that it opposes the cause which produces it. It looked like a very simple statement, right? Even the exam they're asking like state Lenz's law. That's a very simple question. Everybody can study it, but the probability of asking such a question is very less. Instead of that, they will be giving you a situation and you may ask to find the direction of induced current. Here, the real interesting thing is we are inducing current or inducing EMF in a coil or a piece of wire. So, in a piece of wire, look at this. If you are taking this as a piece of wire, how many possibilities are there for the direction of induced EMF? Just check, it's a piece of wire. So, how many possibilities are there? You know that in a piece of wire, there is no chance of flow of current in this way, right? The possibilities are either up or down, or if you are keeping the wire in a horizontal manner, it will be either in this way or in the other way. What does it mean? It's like a 50-50 choice, right? What are the possible directions? Only two possible directions are there, up or down, right or left. But still, it is a very complicated question. It's not easy to find it. Let's check how can we find the direction of induced EMF based on an example. Look at this situation. See, this is a very simple example for inducing EMF in a coil. Look at this. This is a very familiar circuit for you. You can see there is a coil. That coil is connected to a galvanometer and there is a bulb. And please note that there is no source of electricity to the circuit, which means under this condition the bulb is not going to glow. There is no source, there is no battery. Okay. Near to that, there is a magnet. So, according to Faraday's law of EMI, when this magnet is moving towards the coil, definitely there will be a change in flux, right? When the magnet is moving towards the coil, the flux will be changing, and when the flux is changing, there will be an induced EMF. So, definitely EMF will be induced in this coil. So, we are trying to find the direction of induced EMF as per Lenz's law. Let's go back to the statement of Lenz's law. It is stating that the direction of induced EMF is such that it opposes, right? It opposes in the sense, what opposes? Induced EMF opposes. Induced EMF opposes the cause which produces it. Okay, so here, if this magnet is moving towards the coil, induced EMF will oppose the cause. So what is the cause here? That's what you have to think. What is the cause of inducing EMF here? It is the movement of the magnet towards the coil. You can see it clearly. The magnet is moving towards the coil, right? And that is the cause of inducing EMF, right? So look at this situation. You can see the magnet is there, the north pole is there, and it is facing a coil, right? So, what is the cause of inducing EMF? The movement of the magnet towards the coil. So, as per Lenz's law, the coil will try to oppose. So, you may think that how can a coil opposes the movement of a magnet? Remember, when there is a current in a coil or a solenoid, you know that solenoid will behave like a magnet, right? and every magnet has two poles. So look at the situation here. You can see the north pole is moving towards the coil, right? North pole is moving towards the coil, and that is the cause of EMF. So the EMF will try to oppose that cause. So how can an EMF oppose this movement? Okay, be careful. This north pole is moving towards the coil. You know that when a current is flowing through a solenoid, it will behave like a magnet. That means one end will be behaving like a north pole and other will be like south pole. So here this EMF tried to oppose this movement of the magnet, so it will try to oppose the north pole. How can a magnet oppose the north pole? For that, this end of the coil should behave like north pole. How is it possible? You know that when a current is flowing in a solenoid in clockwise direction at one end, that end will be the south pole, and if the current is flowing in anti-clockwise direction, that end will be the north pole, right? So here we need which pole? North pole. For getting north pole, it should behave like, the current need to be flow in which direction? Anti-clockwise direction. Look at the situation. You can clearly see that for a person who is observing from this side, look at the way in which the current is flowing. This is clearly anti-clockwise, right? So it will be behaving like what? North pole, so that it can easily oppose this movement. Is it clear? So when the north pole is moving towards the coil, this will try to oppose it, for that this end will be behaving like north pole by the movement. Okay, now you just look another situation. Here the magnet is moving away from the coil. At that time also there will be a change in flux, right? Magnet is moving away from the coil. At that time, let's see how can we find the direction of induced EMF in the coil. So here, what is the cause of inducing EMF? It is the away movement of the magnet, right? The magnet is moving away from the coil. Which end is moving away? Clearly you can see the north pole is moving away from the coil. So this end of the coil will try to oppose that movement. Try to oppose that movement means it will try to pull it back. Try to pull it back. For that, it should behave like which pole? South pole. I think it is very clear. Earlier, it had to behave like north pole. Now it is behaving like south pole. Then only it can pull it back. So for getting south pole, in which way the current need to be flow? Current should be flow in clockwise direction, right? So for a person who is observing from this side, the current in this coil has to be flow in which direction? Clockwise direction. Okay, when the magnet was moving towards it, hope you remember, the current was flowing in anti-clockwise direction. When the magnet is moving away from it, the current has to be flow in clockwise direction. So what we are getting is, in one movement, when the magnet is moving in one direction, we are getting one direction for the current. When the magnet is moving in the opposite direction, the direction of current is also reversed. So it's very interesting, right? So we'll be getting an alternating current, the current which is changing its direction. Hope this is very clear for you, and we will be discussing many questions based on this and many situations based on this in the next session. Hope this class is very helpful for you. Thank you very much. See you in the next class. Bye.